This chapter is primarily about the mechanics of making chemical bonds, and specifically how valence electrons are used to make both ionic and covalent bonds. Later in the chapter, we'll talk about how the bond determines the polarity of the molecule itself and the overall shape of the molecule. Just as a reminder, it is the valence electrons, the electrons in the highest energy shell, that are used for chemical bonding. And as you probably remember, these valence electrons can either be shared between two atoms that are bonding or completely transferred from one or the other, and that determines the type of bond that's made. So it's important to know the number of valence electrons that various elements have. And the easiest way to remember it, I think, is that the valence electrons equal the group number in using the 1A and B numbering system. So group 1A, the alkali metals have one valence. Group 2A, alkaline earth metals, have two valence, and onward. Obviously, helium's an exception. It has a full shell with just 2 electrons, but the rest of the elements in group 8A have 8 valence. We're going to start off the chapter talking about a bonding theory called the Lewis theory, and it's handy, it's useful, and it's pretty simple. We're going to start off by learning how to draw Lewis structures for both elements and molecules. In a Lewis structure, the valence electrons are represented with dots, and the dots are placed around the symbol for the element. So, for example, oxygen, which is in group 6A, has 6 valence electrons, and so we are going to put 6 dots around the symbol for oxygen. Convention typically has that you put 1 dot on each of the 4 sides before you pair them. That's not always the case. Some people have shifted to how they place the dots, but regardless, I'm not going to mark it right or wrong. It doesn't matter where you start on the 4 sides or what direction you go, anything like that, as long as you have 6 valence electrons around oxygen, for example. And just to give you an idea, here is all of the elements in the periodic table with just their valence electrons shown. So these are the Lewis structures of the elements. And as a reminder, all of the elements in one particular group or family have the same number of valence electrons, which is why they have similar properties. The driving force for elements to become an ion or to make any type of chemical bond, whether it be covalent or ionic, is so that they end up with 8 valence electrons. We call that a full outer shell. So the electron configuration that goes with a full outer shell, and that should look more like S2P6, okay, 2 plus 6 is 8. So this electron configuration ending represents a full valence shell. And you will start to notice, hopefully, that if you were to write out the electron configuration for pretty much any ion, they would all end with an electron configuration of S2P6, showing that they are noble gas-like in their electron configuration. So to give you an example of that, let's look at potassium, which is a metal. Metals virtually always give up electrons to become cations, positively charged ion. If you hear breathing, by the way, it is not me, it is my dog that I'm playing fetch with. So if you look at neutral potassium, here's its electron configuration. Potassium's in group 1A. There's 1 valence electron, and so when potassium becomes an ion, as with all of the group 1 elements, it loses the 1 valence electron, and so the electron configuration for potassium cation is right here on the bottom. And as I said before, all ions will end with the S2P6 configuration, showing that they are now like a noble gas with their electrons. Nonmetals to the right of the stair step have a high electronegativity, which means they have a strong attraction for extra electrons. So it is the nonmetals will tend to be electron acceptors or gain extra electrons to become anions. But if you look at the electron configuration for anions, you will see that they also are noble gas-like in their configuration. All right, so this is a process you should be able to do. It is using Bohr diagrams. Remember, Bohr is the one that first suggested that electrons are quantized or must exist in certain energy levels. So here is the Bohr model for a neutral sodium atom and a neutral chlorine atom. And to know how to set that up, you would start out by writing, at least I do, start out by writing electron configurations for each. So sodium would be 1s2, 2s2, 2p6, 3s1. Once you have the electron configuration drawn, you place these electrons in the appropriate energy levels. So Na represents a sodium nucleus. Draw the first energy ring, n equals 1, and place in it 2 electrons. Then in the second energy level, we have 2 plus 6 or 8 electrons. So you would draw your second energy ring and place in it 8 electrons. And finally, in the third ring around sodium nucleus, there is only 1 electron. You would do the same thing for chlorine. And then you would have to remember metals become cations, nonmetals become anions, which means sodium will donate its valence electron to chlorine. Look at now the Bohr models and electron configurations for the resultant sodium cation and chlorine anion. First of all, the outer shell on both of them is full. Okay, the outer shell, the highest energy shell, has 8 electrons for both of these ions. And if you were to look at the electron configurations, they would also both be noble gas-like in their electron. Whoops. Okay, so here's sodium. And chlorine, let's see, 2s2, 2p6, 3s2, 3p6. So both the ions end in s2p6 configurations. You can also show the formation of sodium chloride quite easily using Lewis structures. So the Lewis structure for neutral sodium has 1 valence, so there's only 1 dot, and neutral chlorine has 7 valence. Then you would use an arrow again to show that sodium donates its valence electron to chlorine. And now this is important to listen here because this is an easy question to forget. We will spend the rest of the chapter talking about Lewis structures for pretty complex covalent compounds. So you're going to kind of forget about Lewis structures for ionic. So make a note of this. Anytime you draw cations, the Lewis structure for a cation, you show the cation as having no dots. I just say it's a naked cation, okay? And that just implies that it gave away its valence electrons. Of course, don't forget the charge. Then anions are always shown as having 8 valence electrons or 8 dots around it. All right. This is a typical question I might ask on your next exam, and so if you didn't already do this in class, you should try to do it now. See if you can draw a Lewis structure for magnesium chloride. Now, before you start drawing Lewis structures of ionic compounds, you're going to want to know what the formula for the ionic compound is. And that is always a two-step process where you assign charges and do your crisscross, and you would see the formula for magnesium chloride has 2 chlorines. So before you can go drawing the Lewis structure showing the formation of magnesium chloride, you would have to know there are in fact 2 chlorines. And so you would finally show it like this. All right, so we talked about ionic bonding, and we're going to talk about covalent bonding Lewis structures now, which get quite a bit more complex. Remember that a covalent bond is when valence electrons are shared between 2 atoms rather than totally transferred. The net result, though, whether it be covalent or ionic, is that the atoms end up with a full outer shell, okay, or an octet of valence electrons. So just a little bit about vocabulary. Here's a Lewis dot structure for water, and rather there is no formation of ions because electrons aren't transferred. So we have what we call bonding pairs. Those are electrons that are shared between 2 atoms. And we also have what we call lone pairs, or sometimes they're called non-bonding pairs of electrons. Okay. But in any case, you can see now, I think, that oxygen has an octet once it bonds. So if you're counting for whether or not an atom has an octet in a molecule, you count all of the electrons around it. So it'd be 2, 4, 6, 8. Also, real quick before I forget, it's perfectly fine to draw the Lewis structure of water like that, but it's also perfectly acceptable to swap or to represent a bonding pair of electrons as a single line. So it would be okay to draw the Lewis structure for water like this. You still have to show the non-bonding electron pairs, but you can replace the shared bonding electrons with single lines. All right, so we can, atoms can either share one pair of electrons between them, which makes a single bond. So every single line you see represents 2 electrons. I'm sure you've heard of a double bond, okay? So sometimes atoms will share 2 pairs of electrons, or a total of 4 electrons between them, in order to get an octet. And so molecular oxygen is an example of that. Each neutral oxygen atom has 6 valence. So in order to have a full outer shell, which is 8 valence, each oxygen needs to gain 2 electrons. And they do so by each of them sharing 2 electrons with each other. So again, each pair of electrons can be replaced with a line, and since we have 2 pairs here, it's 2 lines or a double bond. And finally, you can also have triple bonds, and that's just simply 6 electrons or 3 pairs that are shared between 2 atoms, and diatomic nitrogen is one of those cases. That's it for this first PowerPoint.